In general, there will be no killing vectors at all with which to define positive frequency modes. This is a sentence on page 45 of Birrell and Davies' Quantum Fields in Curved Space, the canonical textbook on quantum field theory in curved spacetime, published in 1982, still in print, still taught. It says, in passing, that once spacetime is curved, which is to say, once you leave flat Minkowski and enter the actual universe, there is no canonical way to decide what counts as a positive frequency mode and what a negative frequency mode of a quantum field. And without a canonical positive frequency mode, there is no canonical vacuum. This is not a controversial claim. It is in the textbook. It has been in the textbook for over 40 years. What I want to convince you of in the next 15 minutes or so is that this quiet sentence and the cosmological constant problem and the dark energy puzzle that has only sharpened with Daisie's data release this past year, that all of these are the same problem wearing different hats, and that we already know how to solve it. In fact, we have known for the better part of a century. We have just been quietly embarrassed about the solution. Dark matter and dark energy are the names we have for two robustly established series of observations, two empirical facts. First, the universe contains more gravitating stuff than the stuff that radiates. This is dark matter. This is settled. This has been clear since Zwicky's coma cluster analysis in the 1930s and Vera Rubin's galactic rotation curves in the 1970s. Second, the universe is expanding in a way that requires either a cosmological constant or something that behaves like one, and the latter requirement is, currently, in some tension with the data. For about 100 years now, more or less since Hubble in 1929, we have known that the universe is expanding. For about 30 years, since the supernova surveys of Rees and Perlmutter in the 1990s, we have known that this expansion is accelerating. The Nobel Prize for that observation was awarded in 2011, and just over a year ago, the team behind the Dark Energy Spectroscopic Instrument, DESI, released a dataset in which the simplest model of accelerating expansion, namely a single lambda that remains constant for all time, no longer quite works. The data prefer a lambda that evolves with time. The deviation is at about 3 sigma. It is not yet a discovery, but the situation is no longer comfortable for the cosmological constant. Famously, the cosmological constant was first introduced by Einstein shortly after his field equations of 1915, in a 1917 paper trying to recover a static universe. Einstein's equations relate the curvature of space-time to the energy and momentum it contains, but the equations admit mathematically of an extra term, a constant term, multiplying the metric. Einstein included it, then took it back out, then put it back in again, arguably by accident. This is lambda, the cosmological constant. Here is the thing about lambda that is worth saying out loud. It is an integration constant, just a more generalized and abstract version of the type of integration constants that should be familiar from high school calculus. The Bianchi identities of general relativity, which are the conservation law for the geometric side of Einstein's equations, fix the equations up to a constant of integration, and that constant is lambda. Nothing in the structure of general relativity itself selects a value for it. Not zero, not positive, not negative. The theory permits all three. Positive lambda yields an endlessly accelerating universe of the de Sitter type. Negative lambda yields a decelerating universe that eventually collapses in on itself, anti-de Sitter. Lambda equals 0 is the flat Minkowski limit. These are very different cosmologies, but the general theory of relativity doesn't say which one is correct. It simply describes all three. In physics folklore, lambda is sometimes called dark energy, but that is a name, not an explanation. What we actually have is an integration constant in a 100-year-old theory whose value is dictated by observation rather than by principle. Our observations have been somewhat strange for at least 30 years, and they have possibly gotten even stranger over the past year or two. However, much of this confusion may be avoided if we drop the folklore and stick to the math, because Mathematically, the function of lambda is clear. Mathematically, lambda describes what you could call the intrinsic curvature of the vacuum. The cosmological constant problem is, in reality, a question about the nature of the vacuum, and that is exactly where Birrell and Davies enter the picture. To understand why the quantum vacuum is so hard to pin down, I want to take a detour through ordinary quantum mechanics. But to be clear, this isn't really a detour. It's the exact same problem, just earlier in the logical chain. Quantum mechanics has a peculiar relationship with time. For every other observable, position, momentum, energy, there is a self-adjoint operator. Self-adjoint operators are how quantum mechanics encodes things you can measure. So, using the tools of quantum mechanics, we can measure, to within certain limits, position, momentum, and energy. But there is no self-adjoint time operator. You can't write a self-adjoint operator t satisfying the canonical conjugate relation t, h equals I h bar. This isn't because nobody tried. Pauli proved in 1933 that you can't. The argument is short and brutal. If such a t existed, then e to the negative iat over h bar would be a unitary operator translating the spectrum of h by a. But h is bounded below. Every stable physical system has a ground state energy, i.e., a vacuum. Unitary translation by an arbitrary amount cannot leave a bounded below set bounded below. Contradiction. There is no such t. So, in ordinary quantum mechanics, it is, strictly speaking, impossible to measure time. More precisely, in the standard formulation, time is not a measurable, not something you can meter, but is instead a parameter. Most commonly, time is just the label on the wave function psi of t. Specifically, it is the parameter we use to measure how the wave function evolves. The standard reading of Pauli's theorem is, time is special. Time is different. Time is a parameter, not an observable, and that's just the way it is. We have learned to live with it. Except, atomic clocks exist. Atomic clocks measure time the way other instruments measure momentum or energy. They return a number with an uncertainty, and the uncertainty satisfies a relation that looks an awful lot like delta E delta t is greater than or equal to h bar over 2. We measure time as an observable in the laboratory routinely, with more precision than almost anything else we can measure. Pauli says no. The laboratory says yes. We have been living with this disagreement for 90 years. But notice what Pauli's argument actually depends on in terms of the underlying logical and mathematical machinery. The hypothesis is that the Hilbert space has a positive definite inner product. That's where bounded below gets its bite. Bounded below relative to a positive definite norm. Drop the positive definite hypothesis and the theorem doesn't run. One more point about time before we go on. The time parameter t in psi of t is real valued. Just real valued. It is a number incrementing forward. It is not Lorentzian, not Euclidean, not anything else. The Lorentzian or Euclidean character we sometimes attach to time is not a property of time itself. It is a property of the structure we put on the dynamics. Wick rotation, which takes you between Euclidean and Lorentzian formulations, doesn't do anything to time as a parameter. It rotates the contour the parameter sits on and changes what algebraic structure you're computing with respect to. Time itself is unchanged. We will return to this point shortly because the positive definite structure that breaks Pauli's theorem is exactly the structure that Wick rotation is rotating in and out of. So now let's go back to the textbook page at the start. When Birrell and Davies say that, quote, in general there will be no killing vectors at all with which to define positive frequency modes, this is what they mean. In flat Minkowski spacetime, time translation symmetry gives you a canonical decomposition of fields into positive frequency and negative frequency components. That decomposition defines the vacuum. The vacuum is the state annihilated by all the negative frequency lowering operators. But in curved spacetime generically, there is no time translation symmetry. That is to say, in general, in curved spacetime, there are no killing vectors at all. So the canonical decomposition fails. Different choices of, quote, time direction give different positive frequency modes, and therefore different vacua. Put somewhat differently and perhaps poetically, the vacuum is not a property of the spacetime. It is a property of the observer. But in fact, you don't even need curved spacetime to see this. You can see it in flat Minkowski space just by choosing a non-inertial observer. On page 115, Birrell and Davies write, quote, hence the Rindler modes, by virtue of their non-analyticity, cannot be a combination of pure positive frequency Minkowski modes, but must also contain negative frequencies. The Rindler observer is a uniformly accelerated observer in flat Minkowski space. They define their own time coordinate, proper time along their accelerated world line, and their own positive frequency modes. And those modes are non-analytic at the Rindler horizon. Therefore, they contain negative frequencies when expressed in the Minkowski inertial basis. Loosely, we could say, rocket fuel turns time-like access into space-like separation. With enough proper acceleration, what looks time-like accessible to an inertial observer becomes space-like separated for an accelerated observer. The Rindler horizon is the boundary. Modes that fell into the inertial positive frequency sector become a mixture, for the Rindler observer, of positive and negative frequencies. This is the celebrated Unruh effect. The Rindler observer sees the Minkowski vacuum as a thermal bath at a temperature proportional to their proper acceleration. So we have two textbook results from the canonical reference for quantum field theory in curved spacetime. One is global. In curved spacetime, there is no canonical killing vector and no canonical vacuum. The other is local. In flat spacetime, change observer and the positive or negative frequency mixes, no canonical vacuum. These are the same statement made at different scales. In other words, there is no canonical vacuum. So the question, what is the vacuum energy, is ill-posed until and unless you ask, which vacuum? And this is what brings us back to the cosmological constant. Because the cosmological constant problem is, structurally, the problem of computing vacuum energy. But there is, in general, no such thing as a unique vacuum. The vacuum energy depends entirely on the choice of vacuum. And every attempt to make the choice canonical has run into the same obstruction. The positive definite structure of standard Hilbert space simply does not accommodate the ambiguity. It tries to force a single answer where the geometry permits a family. Here is the part that I think gets buried in the folklore. The literature has been telling us for 70 years that positive definite is too restrictive. In 1949, Pauli and Villers introduced negative norm ghost fields as regulators, auxiliary fields with, quote, wrong sign propagators that cancel ultraviolet divergences. Pauli-Villers regularization is now standard practice. We have been quietly using negative norm states as calculational devices for over 80 years. In 1950, Suraj Gupta and Gupta-Bleuler, working independently, demonstrated that quantum electrodynamics cannot be quantized in a Lorentz covariant gauge using only positive norm states. The longitudinal photon mode and the time-like photon mode have negative norm. You cannot get rid of them. You can constrain them away from physical observables, and that is what the Lorentz gauge condition does. But the intermediate Hilbert space, before you project to the positive definite subspace, is genuinely indefinite. This has been published in every textbook on quantum field theory ever since. In 1976, Becky, Rouet, and Stora, and independently Tutin, so BRST, did the same thing for non-abelian gauge theories. Covariant quantization of non-abelian gauge theory requires ghost fields with the so-called wrong spin statistics relation and an indefinite, that is, positive-negative metric. The physical spectrum is the BRST cohomology, a subspace of an indefinite metric space, picked out by a nilpotent symmetry operator. This is required for renormalizability and for the unitarity of physical S-matrix elements. You cannot do non-abelian gauge theory without it. In 1978, Gibbons, Hawking, and Perry discovered that the conformal mode of the metric in Euclidean quantum gravity has the wrong sign kinetic term. The path integral is unbounded below in the conformal direction. This is the famous, quote, conformal factor problem. Their resolution is to rotate the conformal mode contour into the imaginary axis, which is to say, the conformal mode is integrated with an indefinite metric, only dressed up as a contour choice. The path integral converges because, secretly, the conformal mode is a negative norm degree of freedom. And then in 1998, and this is the one I really want you to hold in mind, Carl Bender and Stefan Böttcher publish a paper in Physical Review Letters. Their claim is that there exists a large class of non-Hermitian Hamiltonians whose spectra are nevertheless entirely real. The Hamiltonians satisfy a different symmetry, parity times time reversal, PT, but they are not Hermitian in the standard inner product. Nevertheless, they have real spectra. How? Because self-adjointness in quantum mechanics is defined relative to an inner product. Switch the inner product to what is now called the CPT inner product, or equivalently a Krein metric, and operators that look non-Hermitian in the standard inner product become self-adjoint in this new one. Same operators, different inner product, different notion of self-adjointness. And here is what that costs. Pauli's theorem, the 1933 result we walked through earlier, says that in a positive definite Hilbert space with H bounded below, there is no self-adjoint operator T conjugate to H. Bender and the people who followed him have shown that in PT-symmetric quantum mechanics, with its modified indefinite inner product, you can construct exactly such an operator. The theorem isn't violated, rather, its hypothesis is dropped. The escape hatch is to stop insisting on positive definiteness. This is not only a theoretical question. The indefinite character of the quantum vacuum is empirically active in the laboratory. The Casimir effect occurs when two uncharged conducting plates in a vacuum attract each other. This happens because the vacuum energy inside the empty space between the two plates is less than the vacuum energy outside. Less than the vacuum outside, which is to say negative relative to the reference. Lamoureux did the precision measurement in 1997, and the agreement with theoretical predictions has only sharpened in the decades since. Negative energy density, measured with a force gauge. We also observe Wigner function negativity for Fock states. The Wigner function is the quantum mechanical analog of a phase space probability density, and for any classical state, it is non-negative. For a single photon Fock state, the eigenstate of the number operator with eigenvalue 1, the Wigner function at the phase space origin takes the value of negative 2 over pi, approximately negative 0.64. To repeat, the quasi-probability for a single photon to be at the phase space origin is a negative number. Negative. Lvovsky and collaborators measured this directly in 2001 by homodyne tomography. Negative quasi-probability, measured with a quadrature detector. The indefinite character of the quantum vacuum is not a formal artifact of how we set up the math. It is in the lab. It has been measured, directly, experimentally, for decades. So now let's put it all together. We started with the dark energy puzzle. I told you that the cosmological constant is an integration constant, and that what kind of object lambda actually is depends entirely on what we mean by, quote, the vacuum. Then we looked at the canonical texts. The literature states that the vacuum is not unique. There is no canonical positive frequency split in curved spacetime, and not even in flat spacetime once you let your observer accelerate. And there is a readily identifiable pattern running across these results. The mathematical assumption that there must be a unique, positive definite vacuum is the exact same assumption that prevents time from being unobservable. It is the same assumption that forces Euclidean quantum gravity into the conformal factor problem. And it is the same assumption that we have had to quietly drop at intermediate stages of every serious calculation we make in gauge theory. Meanwhile, the indefinite metric is not speculative. It has been the load-bearing structural component of quantum electrodynamics, of non-abelian gauge theory, of curved spacetime quantum field theory, and of Euclidean quantum gravity for the better part of a century. The components are in the literature, peer-reviewed, decades deep. And they have been validated in the laboratory over and over again for decades. The escape hatch from Pauli's theorem is the same escape hatch from the conformal factor problem, which is the same escape hatch from the positive-negative frequency ambiguity in Birrell and Davies. In conclusion, solving the cosmological constant problem doesn't necessarily require inventing a brand new framework or any new mathematics. As a growing body of work in PT-symmetric quantum mechanics and indefinite metric field theory suggests, the pieces may already be on the table. The physics community has known how to do calculations in indefinite metric spaces for a long time. The next step in understanding the vacuum might simply be to look at the math we are already using and ask, what happens if we stop apologizing for it? Thank you very much for listening, and please note this is part of the initiative by Theories of Everything with Curt Jaimungal with the core number 1. Thank you.